Hey, and welcome back to a series I'm doing in complex analysis. Today we're going to be working with the following problem. Suppose we have some polynomial. I've written out its coefficients as these ANs or AIs, if you will. It's degree n, where n is larger than 1. All these AIs are complex numbers, and their modulus is greater than 1, and that's the key fact. So basically, we just have some complex polynomial where the coefficients are outside the unit disk. And what we're asked to show down here is that there exists some w in C, some complex number, such that it has modulus greater than 1, and it's a zero of our polynomial. So in other words, we have a zero of our polynomial that lies outside the unit disk. And so I claim that the tool we're going to be using today is a variant of the fundamental theorem of algebra, and you've probably seen this before. It's basically proved in almost every math class I've ever taken. And there are many different ways to prove it, but I'll just state it informally to kind of remind you what it means. So informally, the fundamental theorem of algebra says that any complex polynomial, so that's just a polynomial with complex coefficients, factors completely over the complex plane. So that's a really nice result, because that means that our polynomial up here, P of z, regardless of what these ANs are, it means we can factor it. Okay, so the next thing we want to think about is how we even want to approach this proof, right? And the key piece here is that we're trying to show something exists. Well, at least most of the time, unless you have a theorem that pertains specifically to existence, showing the existence of some number with a certain property amounts to kind of constructing that number. But this is kind of hard to do, right? Because we don't really know anything about these AIs, these coefficients here, except that their moduli are greater than 1. So sometimes if that seems hard to do, the way to do it is just to start with a proof by contradiction. So why don't we try that? So BWOC, that's by way of contradiction, assume no W exists. So that is all the zeros of P are in the unit disk, which I'll write like that. Okay, well, by the fundamental theorem of algebra, we know P of z factors, and I can write it like this. This is my sign for a product, just like you have your sign for a sum. We have z minus ai, and we have I from 1. Well, I guess I shouldn't write ai because I've already used a. Let's call it bi. I from 1 to n, right? Because it's a degree n polynomial. So we know we have n zeros by the fundamental theorem of algebra, so we can write P of z like this, some bi's. And then the question is, where is our contradiction? So how do we find that? Well, this expression here is really just some numbers, right? Z to the n plus some stuff. And then what's the very last term? It's going to be a product of all of these bi's, 1 to n, and then maybe there's some out here, maybe there's some minus 1 to the n kind of thing, since we wrote it as a negative over there. So this last term here has no z coefficient, but we know it's equal to P of z, and we actually had that formula for P of z. So we know that this term, or this whole sum, right, is equal to our original sum made up of the AIs, and I'm just omitting a lot of terms there by writing my dot, dot, dots, my ellipses. And down here, if we're matching the coefficients of the same degrees, then we know that I get, this is true. Okay. Well, what are we really trying to show? Again, we're trying to show some contradiction, and we have to look back at our problem. What's the fact we haven't used yet? Well, it might be screaming its head at you, but right here, it's just this modulus fact about these AIs being greater than 1. So why don't we just take the modulus of both sides of this equation, and then we get the following. The minus 1 goes away because it was just annoying to begin with. We get those BI's back, and we know that that's true, right? Because this is true for all of our i's. So this is in the problem statement. This is our one of our assumptions. And down here, this product of the BI's, well, we just assumed by way of contradiction that P of Z has no zeros outside the disk, which means that for all BI, the absolute value of BI is strictly less than 1. Well, hang on. We're starting to get perhaps the makings of a contradiction here. And maybe you already see it, but I'll just write it out for you. We can bring this in because this is multiplicative, and it's just the same 1 to n here. But each of these is less than 1, so really the product should also be less than 1, because when we multiply numbers less than 1, we get that. But we just got that 1 is strictly less than itself by following this chain of logic. And that's a contradiction. So in other words, we have found, or rather there must exist, some complex number which is a zero of our polynomial p, which lies outside the unit disk.